Welcome to Shri Learning Academy. Let's simplify priority scheduling algorithm. Imagine a situation where not all tasks are equal. Some tasks are urgent, some are important, and some can wait. Now think about your computer doing the same thing. At any moment, there are dozens of processes waiting for CPU time. But how does the system decide which one should go first? This is where priority scheduling comes into play. And it introduces a very practical idea. Not all processes are treated equally. In priority scheduling, every process is assigned a priority value. This value determines how important that process is compared to others. The scheduler always selects the process with the highest priority for execution. Now, the meaning of highest can vary depending on the system. In some cases, a smaller number means higher priority, like priority 1 being more important than priority 5. In other systems, it can be the opposite. But the core idea remains the same. The CPU gives preference to more important processes. This is very useful in real world scenarios. For example, a system process handling keyboard input or system interrupts should run before a background music player. Otherwise, your system would feel unresponsive. Let's make this clearer with an example. Imagine three processes P1, P2, and P3. Suppose P1 has priority 1, P2 has priority 3, and P3 has priority 2. If all of them arrive at the same time, the CPU will first execute P1 because it has the highest priority. After P1 finishes, it will choose between P2 and P3. Since P3 has higher priority than P2, it will run next, followed by P2. This makes the system behave intelligently by giving preference to more critical tasks instead of just following arrival order like FCFS or shortest job like SJF. Now, priority scheduling can be implemented in two ways: preemptive and non preemptive. These two approaches decide what happens when a new process arrives while another one is already running. This is where things get interesting because the behavior of the system changes significantly. In non preemptive priority scheduling, once a process starts executing, it continues until it finishes or goes into a waiting state. Even if a higher priority process arrives in the middle, it has to wait. The currently running process is not interrupted. This makes the system simpler and easier to manage, but it can sometimes lead to delays for important tasks. For example, imagine a low priority process is running a long computation and suddenly a high priority process arrives, like a system update or an urgent user input. In a non preemptive system, the high priority process has no choice but to wait until the current process finishes. This can affect responsiveness. Let's take a simple example. Suppose P1 starts executing with a low priority and has a burst time of 10 units. After 2 units of time, a new process P2 arrives with a higher priority. In a non preemptive system, P2 will still have to wait until P1 completes its entire execution. Only after P1 finishes will P2 get the CPU. So even though P2 is more important, it is delayed. This shows one of the limitations of non preemptive priority scheduling. On the other hand, in preemptive priority scheduling, the system behaves more dynamically. If a new process arrives with a higher priority than the currently running process, the CPU immediately switches to the new process. This switching is possible because of context switching, which we discussed earlier. The current process is paused and the higher priority process starts executing right away. This makes the system more responsive, especially for critical tasks. Let's revisit the same example. P1 starts execution with low priority. After 2 units, P2 arrives with higher priority. In a preemptive system, P1 will be interrupted immediately and P2 will take over the CPU. Once P2 finishes, P1 can resume from where it left off. This ensures that important tasks are handled without unnecessary delay. This is why preemptive scheduling is commonly used in real time and interactive systems where responsiveness matters. However, this flexibility comes with a cost. Preemptive scheduling involves more context switches, which means more overhead. The system has to save the state of the current process and load the state of another process frequently. If this happens too often, It can reduce overall efficiency. So while preemptive scheduling improves responsiveness, it also increases system complexity. Another important issue that arises in priority scheduling is starvation. This happens when low priority processes keep waiting indefinitely because higher priority processes keep arriving. Imagine a system where high priority tasks are continuously added. A low priority process may never get a chance to execute. This is a serious problem because every process should eventually get CPU time. To solve this, operating systems use a technique called aging. In aging, the priority of a process gradually increases the longer it waits. So even if a process starts with low priority, its priority will improve over time, ensuring that it eventually gets executed. This balances fairness and priority, making the system more practical. Priority scheduling can also be either static or dynamic. In static priority scheduling, the priority of a process is fixed when it is created and does not change. In dynamic priority scheduling, the priority can change based on factors like waiting time, CPU usage, or system requirements. Modern operating systems often use dynamic priorities because they adapt better to changing workloads. To connect this with what we learned earlier, think about how this differs from algorithms like SJF or round robin. SJF focuses on burst time, round robin focuses on fairness using time slices, but priority scheduling focuses on importance. Each algorithm solves a different problem. Priority scheduling is particularly useful when certain tasks must be completed urgently, like system level operations or real time applications. In real world systems, priority scheduling is often combined with other techniques. For example, a system might use priority scheduling along with time slicing to ensure both fairness and responsiveness. This hybrid approach helps overcome the limitations of using a single algorithm. So, if we step back and look at the big picture, priority scheduling introduces a smarter way of managing CPU time by considering the importance of processes. The difference between preemptive and non preemptive versions lies in how aggressively the system reacts to new high priority processes. Non preemptive scheduling is simpler but less responsive, while preemptive scheduling is more dynamic but comes with additional overhead. Understanding this difference is crucial because it forms the foundation for more advanced scheduling techniques that we will explore next. That is it for this video. See you in the next one.